the biggest resin 3D printer I've ever seen.
We've manufactured parts as big as a truck dash. The best thing about having a big machine is doing 200 or 300 parts in one go rather than having to do it one at a time as you would on your own.
Resin 3D printing opens up a few different use cases compared to the more conventional plastics 3D printing, and the machines are getting more accessible at an enthusiast level, but what we've got here is the biggest resin 3D printer I've ever seen. Can you explain what this monster is and how this technology actually works?
This is the Pro X800 from 3D Systems, and it's the SLA, which is stereolithography. So we've got 400 litres of resin in the bottom, we've got a laser at the top, and an elevator in here, which is basically the build platform. And the reason we have this and what it's for is, like any other 3D printing, it's for prototyping. That's its main function, mainly because it's especially historically, they had quite limited materials as far as UV exposure and that goes. But more recently, now we're manufacturing off these with much better materials.
Okay, so just to talk through the kind of process, the resin is obviously initially in a liquid form, and then it's cured using UV light into a solid polymerization, I guess.
Yeah, so it is photopolymerization, so we've got sensitive resin, but we've actually got a laser up in the top. So what's happening is the laser's firing horizontally, pinging off mirrors, same as other laser technologies, SLS and powder bed and like the metal machines. But where the laser hits the surface of the resin, it's then solidifying that liquid resin and turning it solid. And so it's the cross-section, again, like any other 3D printing technology, we've got a cross-section over a 3D object, and it's just drawing that cross-section as a vector sort of thing.
Yeah, cool. So, like we discussed before, you've got these SLS machines here. I mean, FDM, FFF is also possible. Why use resin other than that? What were this kind of more specific use cases where resin would be an advantage over more thermoplastic-based stuff?
Biggest reason is surface finish. Okay. And so we get a much nicer finish on these, even though, again, this operates at about 100 micron. Our smaller machines, DLPs, still resin-based, we can get them down to 10 micron. So you're talking really fine detail, but really nice, like a gloss-like finish you're getting off this machine. So when we go to secondary uses like vacuum casting of urethanes and silicons and taking silicon molds and all that, the cleanup on these parts is minimal. Absolutely minimal compared to using an SLS or an FDM, but also that fine feature is so much better. The support structures are very fine as well because this is going down. There's not much force on the part during printing, so the contact point on the part is much smaller than a vertical print as well.
Inverted setup.
Correct. Yeah. That's another big advantage just from post-processing point of view.
Okay, cool. So use cases, I mean, prototyping, final parts there, but you also talked about tooling as well. In terms of the properties of the actual parts as they come out compared to, I know it's going to depend on the specific resin and the material you're using, but if we compare that to, an SLS part, is there anywhere where it's better or worse?
Depending on what you want to use it for, we've got a clear material, for instance, that's got incredibly high clarity. And so we use that for lens prototypes and anything you want to see through and do fluid analysis and stuff like that. The other properties can be, if the SLS is a nylon, it's more like an ABS type. So we've probably got just a slightly different property, way more rigid than nylon of the same thickness. But you can also get into other applications like, we don't run them ourselves, but when you get into composites and having parts that can actually be heated and extracted, there's some that have been formulated for that. There's also a material, our clear material that I mentioned, is also an investment casting material. Okay. So we can do master patterns on this and then get parts, send that to the foundry and then have parts cast into metal as well as a different way of making metal parts.
Definitely functionally and I guess aesthetic reasons. In terms of like the temperature resistance of the resins, if you use a high temperature resin, is that going to be a viable option for anything in the engine bay of a race car, for example?
You can. Again, there is formulations for those high temperature applications, definitely. As a bureau, we've sort of picked the middle of the road material. Like, again, we've got 400 litres of resin, so we don't just swap it out willy-nilly, so we're going to have something that does most things but not everything. So this is the material that's in here at the moment, is one that we call Extreme. It's an ABS type material, and it's heat deflections down sort of into that 50, 60 degree territory. So that's not going to be suitable for under the bonnet, but there is materials on these platforms that the Formula One guys and NASCAR and all those guys use, definitely.
Yeah, cool. All right. You just mentioned the 400 litres of resin, and I think anyone who's familiar with resin printing and how much a litre costs can probably do the maths there, so we won't get into that too deep. But the actual size of the parts that you can print on this, what are we kind of talking?
So the actual build chamber here is 750 millimetres by 650 by 550.
Okay.
So it's a nice big chamber. We've manufactured parts as big as a truck dash, but we've split that dash into 3 pieces, but then we've nested all 3 pieces together in one print.
Yeah.
So it's nice and big. So we've done big parts, but I think the best thing about having a big machine isn't doing big parts, it's doing lots of little parts at once. And that's the bit I think people forget about. So you can do, again, 200 or 300 parts in one go rather than having to do it one at a time as you would on your own desktop machine.
Yeah, and if we talk about that from production efficiency, obviously doing multiple parts at the same time is going to save the time overall. If we talk about the actual speed of a printer like this, surely it's got to be running a little bit slower than, the small desktop unit?
Yes and no. The main limitation on this is actually it recoats every layer.
Oh, okay.
And so the time that takes to do that is where the time accumulation comes from. The actual scanning time is quite minimal. So if you can get lots of parts in there, we're snapping through pretty quick. So for a Z height, not quite, but I'm pretty much the same speed for doing, say, 10 parts as I'd be for maybe 100 or so.
Yeah.
So again, it's in our best interest to have this thing loaded up as much as possible.
Cool.
Yeah.
And the actual technology that's being used by the printer also has a big effect on the speed of it as well. And I'd like to you mentioned the DLP printers that you have.
Yeah.
We just walk around to those now and have a little look. Yeah, so how does the DLP technology differ from SLA for starters?
This is operating a lamp underneath. So rather than being a laser like SLA, we've got a lamp underneath. And on this particular model, the bottom of the resin tray is clear. And then it's digitally projecting that light up pixel by pixel. And so it's masking, turning pixels on and off, and that exposure of the light to the resin is what's curing that resin from liquid to solid.
So in this case, you'd be able to expose the entire cross-section at once where that's tracing it out essentially.
Exactly right. So this standalone machine here is a smaller example of it. There's a large machine that's just come onto the market from 3D Systems. It's got quite a much bigger chamber. And that advantage is to say one part takes the same amount of time as 100 parts for the same cross-section.
Yeah.
So the speed is, so impressive.
So just to kind of summarize that a little bit more, I guess if we talk about FDM, it's got to trace around the outline of all those parts.
Yep.
But if we're just like doing the same speed for every layer, it's obviously advantage to lay out the whole build plate.
Dead right.
Okay, in terms of the part, actually, typically CAD model through a slicer into this machine, it prints it for you.
Yep.
After that's finished, where do we go from there in terms of post-processes?
So like SLA, this will have a support structure on it,
Yep.
and it'll be anchored to the plate. So we've got a decision about whether we keep it on the plate through post-processing or take it off. So that's the first thing. And then we have to remove our liquid resin. So we go through a bath, an ultrasonic bath to take all that resin off. Once that's done, then we take it to a UV oven, and that does the final curing and really bakes in those mechanical properties.
Yeah, right. So the part straight out of it, is that in what's called like a green state where it's not fully cured?
Yep, dead right. Yep.
Okay.
So they're still quite sensitive at that stage, and you've got to be careful that they're not usable at that stage. Definitely need some work.
Is that the case for every resin material that you're using?
Everything that we're running, or everything has to go through that process.
Cool.
They all have different curing times, but they absolutely need some level of UV exposure. And I think the thing that's interesting with some of the materials that we've got is, although they're cured in UV, we then have UV resistant materials. So the beauty of the material portfolio that we've got with 3D Systems is we're talking end-use materials. It's not just prototyping. And we're right into biocompatibility, embedment, again, flame retardants, but we're talking 5 to 8 years UV exposure. So proper outdoor use of parts.
Right.
So it's manufacturing, not just prototyping.
So just in that case, because it's cured under UV light, in some cases doesn't mean it's actually going to stand up to UV light.
No, what are you using the part for is the most important question.
Yeah.
So if it doesn't matter, it's normally the cheaper material as well. So if it doesn't need to be, great. Yep.
Yeah. Okay, so the last question I just wanted to touch on would be the actual material once it's cured. So these are Thermoset resins. That differs a little bit from a thermoplastic in that how it responds to heat once it's cured. Can you talk us through that a little bit?
Yeah, so it's essentially that once they are cured off, again, different materials have different properties as far as their heat resistance, but you're not going to be reshaping these or anything. They're pretty much dusted.
Excessive heat, it's not going to melt. It's basically going to break down and degrade. Get brittle.
But in saying that, there's two materials in particular. One's a 150 degree flame retardant, and the other is a 300 degree, which is done especially for electronics. But also high temp, more of a static type application. It's not great with dynamic loading. But is awesome for being like in a clamped sort of a static with real nasty environment.
Okay, cool, awesome. Well, I think that gives us some insight into how the process works and also the use cases and how it differs to more traditional forms of additive manufacturing, I guess. So if people want to follow along with what you're doing, see a little bit more of this, where are they best to do so?
Website's the best, so fiadditive.co.nz, and again, they can jump on there, and if they want to see upload their files and have a play on their online portal, they can do so there.
Cool, thanks for your time.
Pleasure.
Cheers.